A very good noon to one and all. So today the topic is crystallization of metals. So crystallization means it is a process of formation of crystals from molten metal. That means it involves the arrangement of atoms in a repeating pattern, which results in crystal lattice structure. So the crystallization process can be influenced by the following factors such as cooling rate, nucleation sites, and impurities. So the main importance of this crystallization process is in the production of metals and alloys. It is very much used, and the crystallization process can affect the properties of the metal. Those properties such as its strength, ductility, and electrical conductivity, like that. So understanding this crystallization process is very important for controlling the properties of metals and alloys. Suppose for example, when a molten metal like copper, which is cooled slowly, and it forms a crystal lattice structure. So the copper atoms arrange themselves in a structure, one structure. So basically, the copper atoms arrange themselves in a face center cubic structure. That means FCC structure. So which is a repeating pattern of atoms. So these type of structures will be discussed in this lecture too. And coming to the step by step process of this crystallization means, so the first step is nucleation. So nucleation means it is the process of formation of crystal nucleus, which can be homogeneous or heterogeneous. Homogeneous in the sense it is spontaneous, okay, and heterogeneous means it is generally influenced by the impurities or surfaces. So it is nothing but a nucleation. So this is the first step in the crystallization. So after that, next step is growth. So growth means it is the process of crystal growth, so which can be influenced by the factors such as temperature or concentration of impurities and crystal structure. Okay, so by these factors the crystal growth will be happen. So next step is cooling rate. So cooling rate means it is the rate at which the molten metal is cooled, which can affect the crystallization process. Okay, so it is nothing but a cooling rate. It is one important definition in this concept. And a slower cooling rate can result in larger crystals, so while the faster cooling rate can result in smaller crystals. So this is the main important thing regarding the cooling rate. And next step is nucleation sites. Suppose if you observe this, the presence of nucleation sites such as impurities or surfaces can influence the crystallization process. So these sites can provide a location for crystal growth to begin. Okay, so this is the main important thing. And coming to the next step, it is a crystal lattice structure. So the arrangement of atoms in a repeating pattern resulting in a crystal lattice structure. The crystal lattice structure can be influenced by the factors such as the type of material and the cooling rate and what are the impurities are present. So based upon these factors which are influenced uh, in this crystal lattice structure. Okay, so next step is a grain formation. This is the main important thing. uh, Grain formation, the name itself, the formation of grains, which are small crystals in a polycrystalline material. So the grain boundaries are the interfaces between the adjacent grains. Okay, so this is nothing but a grain formation. So the formation of grains. So next one is a grain growth. The growth of grains, which can be influenced by the following factors. What are those factors? Such as temperature, concentration of impurities, and crystal lattice. So this is nothing but a step by step process regarding this crystallization. So once observe the different diagrams, what are the different main steps Here there is a nucleus formation, and next one is there is a grain growth. Okay, so grain boundary, there is a term called grain boundary which separates the two grains. Okay, uh, so this is nothing but a crystallization, the process of crystallization. I hope everyone understood this concept. So we will move on to the next concept, which is nothing but a packing factor. So packing factor is nothing but it is the ratio of volume of atoms in a unit cell to the total volume of the unit cell. That means it is the volume of atoms in unit cell divided by total volume of unit cell. So this is the basic definition of packing factor. So generally it is a measure of the efficiency of packing of atoms in a crystal lattice. Okay. So now suppose if you consider one example, if you consider any one structure, we need to consider the packing factor. Depends upon the unit cell occupied by the atoms, so we can consider the packing factor. So there are different types of structure. So in my lecture sessions I have clearly explained about the packing factor and various types of structures. So in this lecture I am summarizing the crystal structures, its packing factors. So if you consider the simple cubic structure, so in a simple cubic structure each atom is located at the corner of the cube. Okay, so the packing factor for the simple cubic structure is approximately 52 percentage. Okay, so coming to the body centered cubic structure, so in a body centered cubic structure each atom is located at the center of the cube, in addition to the corners. Okay, so that is the difference. So the packing factor for a body centered cubic structure is approximately 68 percentage. Okay, so coming to the next structure, it is a face centered cubic structure. So in a face centered cubic structure each atom is located at the center of each face of a cube in addition to the corners. Okay, so the packing factor for the face centered cubic structure is approximately 74 percentage. Okay, so now coming to the next structure, it is a HCP structure, hexagonal close packed structure. So in a hexagonal close packed structure each atom is located at the center of a hexagon with a hexagonal arrangement of atoms. Okay, so the packing factor for a hexagonal close packed structure is approximately 74 percentage. So as like FCC, HCP also having 74 percentage. Okay, so the main importance of the packing factor is the concept in understanding the properties of materials. So it can affect the density, strength and electrical conductivity of a material. So that's why we need to consider the packing factor for any material. So we have to analyze with respect to its structure. Understood? So this is the concept, brief discussion about the packing factor. So next topic in our syllabus is line density and plane density. So coming to one by one, line density and plane density are generally very important concepts in understanding the crystal structure of materials. So first of all, line density. Line density is nothing but it is a number of atoms per unit length along a specific direction in a crystal lattice. So that means line density is equal to number of atoms divided by length. Okay, number of atoms divided by length. So the main importance for this line density is in understanding the properties of materials such as their strength and electrical conductivity, like that. So this is the main important thing regarding the line density. So we can consider examples like any structure. I am considering FCC. Suppose if you consider FCC structure, the line density along this direction. So we can suppose if we consider 100 direction is 1 atom per unit length. So that is the line density concept. And next one is a plane density. So plane density is nothing but it is the number of atoms per unit area in a specific plane of crystal lattice. So that means a plane density equal to number of atoms divided by area. So line density is number of atoms divided by length. So plane density of the plane perpendicular to the direction. Okay, so the line density along a specific direction is related to the plane density of the plane perpendicular to that direction. So the main importance here, understanding the relationship between line density and plane density is important in understanding the properties of materials. So this is the uh, basic definitions of line density and plane density. Okay, and now coming to the next important topic is nothing but a grain and grain boundary. So these are important concepts in understanding the microstructure of materials. So microstructure of materials means we can consider grain and grain boundary. So first of all, what is a grain? Grain is nothing but a small crystal in the polycrystalline material. Okay, so the grain is the region in a material where the crystal lattice is continuous and unbroken. So this is nothing but a grain. So generally grains have a specific crystal structure and specific orientation and some composition also available for this grain. So these crystal structure, orientation and compositions are basic characteristics for the grain. Okay, for example, if you consider in a piece of copper metal, each grain has a face centered cubic structure. Okay, that is the main beauty of a copper material. Coming to the grain importance, these are very most important in understanding the properties of materials such as their strength, ductility and electrical conductivity, like that. Okay, so this is nothing but a grain. And coming to the next important thing here is a grain boundary. So grain boundary is nothing but it is the interface between two adjacent grains. Okay, a grain boundary is a region where the crystal lattice of two adjacent grains meets. Okay, so these grain boundaries have a specific structure and energy and mobility. So these are the characteristics regarding the grain boundary. Suppose if you consider the same example, copper material, grain boundaries are the interfaces between the adjacent grains. So the grain boundaries are important in understanding the properties of materials such as their strength, ductility and electrical conductivity as like a grain. Okay, so this is nothing but a grain and grain boundary. So what is the main relationship between grain and grain boundary is nothing but grain boundaries separate grains. That means grain boundaries are the interfaces between adjacent grains, and grain boundaries can affect the growth of grains during the recrystallization and grain growth. So this is nothing but a grain and grain boundary. So if you consider the uh, effect of effect of grain boundary and determination of grain sizes. So what are the effect of grain boundary means? Grain boundaries have a significant impact on the properties of materials. So first one, if you consider grain boundary energy, so grain boundaries have a higher energy than the surrounding grain, which can affect the material properties. That is the main important thing. And next one is grain boundary mobility. So grain boundaries can move during the recrystallization and the grain growth, so which can affect the material's microstructure too. Okay. So and coming to the next important thing is a grain boundary segregation. So grain boundaries can segregate impurities which can affect the material properties. Okay. These can segregate impurities which can affect the material properties, right? Okay. So next one is effect on mechanical properties. What are the effects which on mechanical properties regarding grain boundaries? So which can affect the material's strength, ductility, and toughness. So these are the mechanical properties which can affect by the grain boundaries. And next one is effect on electrical properties. If you consider the electrical properties, so it can affect the materials electrical conductivity and resistivity. So and coming to the corrosion resistance, that means effect on corrosion resistance. So these grain boundaries can affect the materials corrosion resistance also. So what is the main important thing I am going to tell is grain boundary is a main important key thing in the materials and its microstructure. So regarding this you have to be noted. So whatever you need to consider for our observation, so please be careful while observing this crystal structure and the grain sizes. Okay. So coming to the determination of grain size, that means how we are going to determine the grain size. So generally grain size is an important parameter in understanding the microstructure of the materials. Okay. So generally there are so many techniques to find out the grain sizes. So uh, what are those techniques I am going to list out here. So first one is optical microscopy. So in this optical microscopy the grain size can be measured by using the optical microscopy, which involves examining the material under the microscope. So this is nothing but a optical microscopy. So everything will be discussed in the lecture sessions in the classroom. So just go through that material. And next one is transmission electron microscopy. The grain in this the grain size can be measured by using transmission electron microscopy, which involves examining the material under a transmission electron microscope. Okay. So coming to the next important technique is X-ray diffraction. So grain size can be measured by using X-ray diffraction, which involves the analyzing the X-ray diffraction pattern of the material. And next one is ASTM grain size number. So grain size can be expressed as an ASTM grain size number, so which is a standardized way of expressing grain sizes. So next one is a grain size distribution. That means a grain size can be expressed as a grain size distribution which shows the range of grain sizes present in the material. So that is the that is also important thing. And the most important importance of grain size is important in understanding the properties of materials, such as their strength, ductility, and electrical conductivity. So it is also a main important thing. Uh, that means while determining the grain sizes, we should be cautious to find out the following factors. Okay. So it's all about different techniques regarding the grain sizes. And next important topic is imperfections in a crystal lattice. So imperfections in a crystal lattice can be point defects, line defects, or plane defects. So if you consider the crystal lattice, there are different types of defects: point defects, line defects, or plane defects. So these are nothing but imperfections in a crystal. So coming to the point defects are nothing but these are the imperfections that occur at a single point in the crystal lattice. Only single point. Okay, single point in a crystal lattice. So in this we can consider vacancies. So a vacancy is a point defect where an atom is missing from the crystal lattice. So it is nothing but a vacancy. Or else we can consider interstitials. So an interstitial is a point defect where an extra atom is present in the crystal lattice. Okay, so vacancy and interstitial elements in the crystal. And next one is substitutional defects. Substitutional defect means it is a point defect where an atom is replaced by a different atom. So that is nothing but a substitutional defects. So effect on these effect on properties like point defects can affect the properties such as its strength, ductility, and electrical conductivity. So it is nothing but a point defects. So coming to the line defects. So these point defects, line defects, and surface defects I have explained clearly in the lecture sessions. So just go through that. So line defects are imperfections that occur along a line in a crystal lattice. These defects are nothing but edge locations, screw dislocations. Okay, so edge dislocations means an edge dislocation is a line defect where an extra half plane of atoms is present. So here a screw dislocation is nothing but where the crystal lattice is twisted. So the crystal lattice is twisted means it is nothing but a screw dislocation. The next defect is plane defects. Plane defects are the imperfections that occur along a plane in a crystal lattice. So these are grain boundaries, twin boundaries, like that. So a grain boundary is a plane defect where two adjacent grains meet. Twin boundaries. A twin boundary is a plane defect where two adjacent grains are mirror images of each other. So this is nothing but a plane defects. So these all are also affecting the properties like strength, ductility, and electrical conductivity. So the main importance of these imperfections is understanding the properties like imperfections can affect the material strength, ductility, electrical conductivity, and some other properties. So these can be used to improve the material properties. That means it can be used to improve the material properties such as its strength and ductility. So it is the main importance regarding the imperfections. Okay, so coming to the imperfections, in these imperfections in detail we need to discuss about this slip and twinning. So slip and twinning are two important deformation mechanisms in the material. So that means slip is a process of plastic deformation by dislocation motion. Okay, so that means slip is the movement of dislocations along a slip plane which result in the plastic deformation. So in these slip systems, slip occurs along specific slip systems which are combinations of slip planes and slip directions. Slip planes in the sense slip planes are the planes along which dislocations move, along which the dislocations move, along which dislocations move. Okay, so slip directions are the directions along which dislocations move. Okay, and the main important thing is a critical resolved shear stress. The critical resolved shear stress is the minimum stress required for the slip to occur. So this slip also may affect the material properties, materials strength, ductility, and hardness. Okay, So this is regarding the slip. And coming to the next point is twinning. Twinning is a process of plastic deformation by the formation of twins. Okay, twinning is the formation of twins, which are regions of crystal lattice that are mirror images of each other. Twinning occurs along specific twinning systems, which are a combination of twinning planes and twinning directions. So twinning planes means these are planes along which twinning occurs. Twinning directions means these are the directions along which twinning occurs. Okay, so this twinning also affects on material properties like material strength, ductility and hardness. So the main similarities, that means both the slip and twinning are the deformation mechanisms that can occur in the materials. So what is the difference between them is slip occurs by dislocation motion, while twinning occurs by the formation of twins. So both the slip and twinning are important